Hello people, this is section 4.7 optimization problems. This is calculus 1 and we are using James Stewart's Calculus Early Transcendentals book, and this is an application of the derivative. So what are optimization problems? Whenever you are asked to find an optimal value, you really are asked to find like the biggest value of something or the smallest value of something. And so far in this chapter, we have discussed techniques of graphing using the first derivative test and the second derivative test. We began the chapter with the ever important extreme value theorem, which allows us to find maximum and minimum outputs on a closed bounded interval. So here's an application where we can optimize things or find the biggest value or the smallest value. And this has very many practical applications in the real world. You know, we might want to minimize the surface area of something. We might want to maximize the area of something that we want to build. We might want to minimize costs, etc. So first, and we're going to use that extreme value theorem, that technique of create an equation that represents the situation that we want to maximize or minimize, and then we will take the derivative of that function, set it equal to 0, find its critical points, go back to what is a reasonable range of values for the variables that we have, and determine if we have a minimum or maximum value. So what are the general steps in solving optimization questions? And I was just speaking just briefly, like, how can you tell if we're asked for an instant rate of change type question, or if we're asked to find a related rate type question, or if we're asked to find an optimal or a maximum or a minimum, so that we can define our processes, okay, of, how to approach the problem. All right, so what are the steps? We want to understand the problem that we're reading. Always with an application question, I always advise my students to follow the problem-solving procedure, which is read the question again, maybe a third time. You want to draw a picture. You want to label that picture with the facts that you know from the problem that you're stating or in the situation that you are given. And by doing so, when you're labeling that diagram, you might want to introduce notation, and usually we want to use symbols that represent what they are, like length. You might want to use the letter L. Area, you might want to use the letter A, the variable A, and whatnot. Second, if you find something in your problem that says find the biggest something that, or find something that will maximize the volume, then you want to figure out what you want to optimize. What do you want to maximize? What do you want to minimize? That is the equation that you want to set up. And sometimes, in order to set up that equation, it might involve more than one variable. Okay, so so it's okay to start with an equation with more than one variable. But then you want to go back to the problem itself and see what other constraints you have. So in the step 5 here, if the Q is what we're calling the thing that we want to maximize or minimize, if that has been expressed as a function of more than one variable, then we use the given information in our problem to find a relationship, in other words, another equation that we can use to actually convert our Q into one variable, because this is calculus of a single variable. Okay, so we want to definitely eliminate all but one of the variables, right? So we use, and I usually call these the constraint equations. Oh, I did a different color. Right, so you want to use your constraints in order to convert your optimization equation into one variable. And then we want to use our extreme value theorem steps. We want to take the derivative of our optimization equation, set it equal to 0, find its critical points, go back to our original equation, and determine if it is a maximum or a minimum. We also want to, at the very end, and I'll add my step 7 here, make sure you answer the question. And what do I mean by that? Sometimes it'll ask for the dimensions of a box that might maximize the area, or it might actually say provide the maximum area. So those are two different ways of responding, but you want to make sure to answer the question. Okay, so I've got a couple of examples here that we will go over to demonstrate the procedure. All right, so we'll start small. Here, this says the sum of two positive numbers is 16. What is the smallest possible value of the sum of their squares? So I recognize this as an optimization question because I have find the smallest possible value of the sum of their squares. That tells me it's an optimization question, and my constraint here is going to be the sum of two positive numbers is 16. So I can write that here. If I'm going to say let x equal the first number and y equal the second number, then I know my constraint here is going to be x plus y is equal to 16. What do I want to minimize? I want to minimize the sum of their squares. Okay, so I'm just going to call it my f of x here is going to equal the sum of their squares. Right? So there's my equation that I want to minimize. And now it's in two variables. So if it's in two variables, I'm going to go back to my constraint equation to get it into one. And so I'm going to say here, if I solve for y, I'm going to get 16 minus x. And I'm going to want to substitute that value inside my optimization equation. So that's going to be x squared plus 16 minus x squared. And now I'm going to want to take my derivative, and now I'm going to optimize. So I'm going to take my derivative, and the derivative of this function is 2x plus, and we have 2 times 16 minus x, but then times the derivative of the inside, chain rule. Now I'm going to clean things up here. This says 2x plus 32 minus, or actually it's minus 32, right? Because we've got a minus on the outside. And then we have minus is a plus, and so we have plus 2x. So when does 4x minus 32 equal 0? We've got when 4x is equal to 32, or 32 is equal to 4x, whichever way you want to see it, or when x is equal to 8. Good. And I can check with my first derivative test, or I can, right? I can see that if I take my first derivative test here in my range of values, if the sum of my positive integers is no bigger than 16, then my range of possible values is 0 to 16 for x and y. And if I put 8 right in the middle, I can pick a test point, right? And my test point here between 0 and 8, I'll pick 1. And between 8 and 16, I can pick 9. And if I take my derivative, and my derivative here was 4x minus 32, right? Then 4x minus 32, if I plug that in, I'm going to get a negative. So that tells me f of x is decreasing. And after 8, if I plug in 9, 9 is 4 times 9 is 36. 36 minus 32, that's positive. So that tells me that my f is increasing. So I've just verified here on the possible rational possibilities for x and y that the value of x equal to 8 is going to give me a minimum, right, for f of x. Good. So it asks, I go back to the question, it says, what is the smallest possible value of the sum of their squares? So I'm going to answer my question what is the value of the sum of their squares here? And so that's going to be my x squared plus my y squared. And since I have 8 squared and y is 16 minus 8 squared, this is going to give me 64 plus 64, 128 is going to be the answer to my question. Good. All right, let's do another one. Here it says, find the dimensions of a rectangle with area 1,000 meters squared, or square meters, whose perimeter is as small as possible. So I'm seeing whose perimeter is as small as possible is telling me to minimize the perimeter. Okay, so that's the equation that I want to find the maximum and minimum of. I want to optimize that. So I already drew a rectangle. I know that the 1,000 square meters is my constraint. And I know that the area is going to equal 1,000 meters squared. And what's the area of our rectangle if I introduce my notation of L and W, which is length times width? This would be L times W equal to 1,000. This is my constraint. And remember, I use my constraint to get my equation into one variable. So what is the perimeter of a rectangle? The perimeter, I can call that P of X for now, equal to 2 times L, or P of L, if I want to say just P here, is 2 times the length plus 2 times the width. That's in two variables. I want one, so I'm going to solve my equation over here and get W here is 1,000 divided by L, or 1,000 times L to the minus 1. So I can substitute this value of W into my equation over here. So I get 2L plus 2 times 1,000 times L to the minus 1, or 2L plus 2,000 times L to the minus 1. So now I'm going to optimize. And I'm going to take my derivative, and the derivative of 2L with respect to L is 2, and then I'll have minus 2,000 times L to the minus 2. That gives me 2 minus 2,000 over L squared. I like to put things in one fraction, so this is going to be 2L squared minus 2,000 all over L squared. And now I want to optimize, and so I'm going to say, when does this equal 0? When the numerator equals 0. So when 2L squared minus 2,000 is equal to 0. And I can solve that. So I get L squared, or 2L squared equal to 2,000, L squared equal to 1,000, and L here is going to equal, yes, it would be true that it's going to be plus or minus the square root of 1,000, but we're talking about positive lengths here. So we would say that it's just the square root of 1,000, and if you want to rationalize that or simplify that, that would be 10 root 10, okay? I go back and I can verify with my checking of my derivative if I want to, or my range of values here. And what are my possible range of values? I can't be more than 1,000, right? So I can't have length times width be more than 1,000 if it's 1,000 meters squared, I don't think. And then 0, so that's just a reasonable type of range, because I'd had 1 times 1,000 could be 1,000 meters, so I don't really want to go over 1,000. It could be 2,000, but really I'm just checking to make sure that I have a minimal perimeter. So if I use 10 root 10, that's a little under 40, so I know that that might be like 36 or something like that. So I'm going to pick a test point. I'm going to pick 1, and then I'm going to pick like 40 here. And my perimeter, my derivative here is 2L squared, or 2 times L squared minus 1,000 over L squared. And if I pick positive 1, I'm going to end up with a negative value, so that tells me that P is decreasing. If I pick 40, 40 times 40 is 1,600. 1,600 take away 1,000 is positive, and the denominator is positive, so I would get a positive here, so that means my P would be increasing. And so I do see that this is going to be a minimum value, or minimum occurrence, right? So it asks, find the dimensions. That's the answer to our question here. Find the dimensions of the rectangle. So our answer is going to be, the dimensions are going to be length times width. And I know that my length is 10 root 10. And I can go back to my constraint with my W. And if I have my W here equal to 1,000 divided by L, 1,000 divided by 10 root 10 is going to be 100 divided by root 10, and that's going to be 100 root 10 over 10, and it's also going to be 10 root 10. So I will have 10 root 10, and what are the measurements? Meters by 10 root 10 meters. So I'm going to get a square. That's going to minimize our perimeter. Good. All right, now let's move on to some fun stuff. Let's say you are offered a pizza, or one slice from a round pizza, in other words, the sector of a circle, and the slice must have perimeter of 32 inches. What diameter pizza will reward you with the largest slice? All right, so here you might need to look up some formulas for sectors and things like that, but I already drew my pizza. You can put pepperoni all over it if you want. From geometry or trigonometry course, we know that the length of the arc, that the round part of your pizza slice, is given by the formula r times theta, where theta is in radians, and radians are real numbers. Okay. If you're offered, and here it says, what diameter pizza will reward you with the largest slice? So we want to optimize the area of the slice. So we want to maximize area of the slice. Okay, what is our constraint? The constraint that we have here is that the perimeter of the slice is equal to 32 inches. So that means 32 would have to be r plus r theta, or 2r plus r theta. Okay, so that's our constraint that will get us to one variable. Now, the area of the slice, I can call A, is given by the equation, or the formula, 1/2 r squared times theta. And that is derived in a geometry or trigonometry course, but you can always look up what's the area of a sector. Okay, well, that's in two variables again. I can go up to my constraint equation, and I can solve, since I want to find the diameter, and we know that diameter is 2 times r, I'm going to solve for theta. So I get here 32 minus 2r equal to r theta, and theta here is 32 minus 2r over r. Okay, so I'm going to take this expression for theta, and I'm going to plug it in here. So what do I get? I end up with 1/2 r squared times, and I'm going to take 32 minus 2r over r. I'm going to clean things up. I know that I can cancel 1r with these 2 r's to leave 1r, and I can factor out a 2 on the 32 minus 2 to give me, this is going to equal r, so I can cancel the 2, right? In other words, I can go 2 cancels with this to leave 16 minus r. Right, so I have my A here is 16r minus r squared, and now we want to optimize, find the maximum. So my process, I want to take my derivative. I want to set my derivative equal to 0, and I see here that 16 is equal to 2r, or r here is equal to 8 inches. Good. So we know that with perimeter, if the perimeter of our slice is no more than 32 and we have 2 r's, r can't go over 16 in order for us to even have a slice. So in our range of values, r would be no more than 16. We can check another way. Instead of doing the first derivative test there, we can go back and use the extreme value theorem on that closed interval, and note that a here of 0, that's our endpoint, right? And our endpoint would be, with our a, if we use this one, a of 16 minus, it would be 16 times 0 minus 0 squared, and that's going to give me 0. Our a of 16 is going to give me 16 times 16 minus 16 squared. That's also going to give me 0. But our 8 of 8 is going to give me 16 times 8, take away 64, and that should give me 64, right? So this is the biggest, and so we know that r is our maximum. And the answer to our question, what's the diameter? Well, the diameter is equal to 2 times r, so it's going to be 16 inches. Okay? And if I plugged in over here theta, just as a note, this is just our answer here. 16 inches will give you the biggest slice, but I just want to give you in a context was how big of a slice would that be. Note that theta here is equal to 32 minus 2r over r. So at r equal to 8, 32 minus 16 gives me 16 over 8 gives me 2 radians. That's roughly equal to 114 degrees. So you're getting about a third of the pizza, just for fun. Yum. Cool? Cool. All right, let's do one more, just in terms of like practicality and stuff. Here we've got a farmer wants to fence in a rectangular plot of land adjacent to the north wall of his barn. No fencing is needed along the barn, and the fencing along the west side of the plot is shared with a neighbor who will split the cost of that portion of the fence. If the fencing costs $20 per linear foot to install, and the farmer's not willing to spend more than $5,000, find the dimensions for the plot that would enclose the most area. So the most area tells me to maximize area. Okay, the spending of no more than $5,000 tells me our constraint is the cost to build the enclosure. And let's just say the farmer's going to do it himself, so he doesn't have to pay for any labor. He just has to pay for the fencing. So what's the cost to build? So our cost here is going to be, if I just go back and label, let's call this X. That means the other side, since it's a rectangle, is going to be X, and we'll call this Y. And I know that my cost will equal $10 times X. That's the shared fence, right? $10 per foot. times the number of feet, right? Plus $20 for the y, per y, $20 per foot times y feet gives me how much money that side will cost. And then again, my own other side, I have to pay $20 per foot as well. I know that the cost can't be more than $5,000. So I would get, and if I collect like terms, I would get 30x plus 20y. Good. So that's my constraint. But they're saying maximize the area. So I'm going to maximize my area. So my A here is going to be x times y. That's two variables again. So I'm going to use my constraint. So with my constraint here, I know if I solve for y, I'm going to get 5,000 minus 30x is going to equal 20y. Y here is going to be 5,000 minus 30x over 20. I can divide by 10 throughout, and if I divide by 10 throughout, I'm going to get 500 minus 3x over 2 is going to equal my y. So I can now transform my y value into an x expression based on the constraint to get area here equal to x times 500 minus 3x over 2. So I can see that my area now, if I just clean things up so I can take derivatives, is going to give me 1/2 times 500x minus 3x squared. Good. And now I want to maximize that. So I'm going to take my derivative, and that's going to give me 1/2, and the derivative of 500x is 500, and the derivative of 3x squared is 6. Good. And now I want to set that equal to 0, right? So I'm going to end up with, this is going to equal 0 when 500 minus 6x is equal to 0, when 500 is equal to 6x, or when x is equal to 500 over 6, or 250 over 3. Good. And that's the length of the side that is shared with the barn as well as the opposite side, right? Notice, and since another way of determining if that is going to be the minimal cost or to, the maximum area, I can tell from just here, my first derivative is 1/2 500 minus 6. My second derivative is going to be 1/2 times 0 minus 6, and that's going to be -3. And since my second derivative is less than 0, it is a concave down. A is concave down. And because it's concave down, my x here at 250 over 3 is a maximum. So I can verify that way as well. So I go back to the question, and it says find the dimensions. So that's how we answer our question. We find the dimensions. So our answer here the dimensions of the enclosure is going to be a length by width, and here that would be y by x, and my y value, I can go back and plug in my 250 over 3, and notice here my y, 500 minus 3 times 250 over 3 over 2 is going to give me 250 divided by 2, or 125. So we're going to have 125, and what are the dimensions? Foot. So it's 125 feet by 250 divided by 3 feet. And that's going to give me the maximum area. All right, hopefully that explains the process for you, knowing how to recognize an optimization question, but then also recognizing your constraints and what you use with those constraints. All right, what's next up? Newton's method. All right, take care.